Hi everybody, welcome to a new PyTorch tutorial. Today we will implement our first multi-layer neural network that can do digit classification based on the famous MNIST dataset. In this tutorial we put all the things from the last tutorials together, so we use the DataLoader to load our dataset, we apply a transform to the dataset, then we will implement our neural net with input layer, hidden layer and output layer, and we will also apply activation functions. Then we set up the loss and the optimizer and implement the training loop that can use batch training. And finally, we evaluate our model and calculate the accuracy. And additionally, we will make sure that our whole code can also run on the GPU if we have GPU support. So let's start. And first of all, we import the things we need. So we import torch. Then we import torch.nn as nn. Then we import torch vision for the data sets, and we import torch vision.transforms as transforms. And we also import matplotlib.pyplot as plt to show you some data later. And then first of all, we do the device configuration, so device config. And for this, we create a device by saying device equals torch.device. And this has the name CUDA if we have GPU support. So if torch.CUDA is available, and if it is not available, so else, we call our device simply CPU. And then later we have to push our tensors to the device. And this will guarantee that it will run on the GPU if this is supported. So yeah, so let's define some hyperparameters. And here let's define the input size. And this is 784. And this is because later we see that our images have the size 28 by 28. And then we will flatten this array to be a 1D tensor. And 28 times 28 is 784. So that's why our input size has to be 784. Then let's define a hidden size. And here I will say this is 100. You can also try out different sizes here. And the number of classes, and this has to be 10 because we have 10 different classes, so we have the digits from 0 to 9. Then let's define the number of epochs, and here I will simply say 2 so that the training doesn't take too long, but you can set this to a higher value. Then we define the batch size here, and this is, let's say, 100. And let's also define the learning rate here by saying learning rate equals 0.001. And now let's import the famous MNIST data. So you can have that from the PyTorch library by saying training dataset equals, and here we use torchvision.datasets.MNIST, and this will have to have the root where it has to be stored, so root equals, and here this should be in the same folder, so dot, and then it should create a folder called data, and then we say train equals true, so this is our training data set, and then we say we apply a transform right away. So we say transform equals transforms dot to tensor. So we convert this to a tensor here. And then we also say download equals true. So it should be downloaded if it is not available already. Then let's copy this and do the same thing with our test data set. And here we have to say train equals false, and we also don't have to download this anymore. So now let's continue and create the data loaders by saying train loader equals, and here we get this from torch.utils.data.dataLoader. And then it will have to have the data set by saying dataset equals, and here it gets the training dataset, so train dataset. Then we have to specify the batch size. So this is equal to the batch size. And then we also have to say, or we can say shuffle equals true. So this is pretty good for training. And then we copy this again and do the same thing for our test loader. So test loader equals, gets the test data set. And we can say shuffle equals false because it doesn't matter for the evaluation. And now let's have a look at one batch of this data by saying examples equals, and then we convert it to a iter object, iter of the train loader, and then we can call the next method and unpack this into samples and into labels by saying this equals examples dot next. And now let's print the size of these. So let's print samples dot shape, and also print the labels dot shape. And now let's save this and run this. So let's call Python feedforward.py to see if this is working so far. And yes, here we have the size of the samples. So this is 100 by 1 by 28 by 28. And this is because our batch size is 100. So we have 100 samples in our batch. Then the 1 is because we only have one channel. So we don't have any colored channels here. So only one channel. And this is our actual image array. So 28 by 28, as I said in the beginning. And our labels is only a tensor of size 100. So for each class label, we have one value here. So yeah, this is our some example data. And now let's also plot this here to see how this is looking. So for I in range 6, and here we use matplotlib. So I call plt dot subplot of the with 2 rows and 3 columns and the index I plus 1, and then I can say plt dot imshow, and here I want to show the actual data, so samples of I and then of 0 because we want to access the first channel. And then I will also give this a color map, so cmap equals gray. And then I say plt.show, and let's save this and run this again. And here we have a look at the data. So these are some example handwritten digits. And now we want to classify these digits. So for this, we want to set up a fully connected neural network with one hidden layer. So let's do this. So let's comment this out again. And now let's create a class neural net. And this has to be derived from nn.module. And now we have to define the init and the forward method. So the init method, so this will get self. And then it will has to have the input size, then the hidden size, and then the output size. So the output size is the number of classes. And here first we want to call the super init. So super of neural net and self and dot init, self dot init. And then we create our layers. So first we want to have a linear layer by saying self.l1 equals nn.linear. And this will has the input size as input, and the output size is the hidden size. Then after the first layer, we want to apply a activation function. And here I simply use the famous ReLU activation. So self.ReLU equals nn.ReLU. And then at the end, we have another linear layer. So self.L2 equals nn.linear. And now we have to be careful. So the input size here is the hidden size, and the output size is the number of classes. And now let's define the forward method. So this will have self and one sample x. And now we apply all these layers. So we say out equals, and now we use the first layer, L1, which gets the sample x. And then the next out is self.relu. Now use the activation function, which will get the previous output here. And the last out equals self.l2 out. So this will apply the second linear function. And now we have to be careful again, because here at the end we don't want an activation function. So we don't apply the softmax here, as usual in multi-class classification problems, because in a second we will see that we will use the cross entropy loss, and this will apply the softmax for us. So no softmax here, so we simply say return out. So this is our whole model, and then we can create it here by saying model equals neural net, and this will get the input size, then the hidden size, and the number of classes. So yeah, now we have the model. So now let's create the loss and the optimizer. So here we say criterion equals nn.cross entropy loss, and this will apply the softmax for us. So that's why we don't want this here, so be very careful about this. And now let's create our optimizer as well by saying optimizer equals torch dot optim dot. Now let's use the Adam optimizer here, and this has to get the parameters, and here we can use model dot parameters. And it also has to get the learning rate, LR equals learning rate. Now we have the loss and the optimizer. And now we can do our training loop. So training loop now. And for this, let's first define the number of total steps. So n total steps equals, and this is the length of the training loader. So now we can do the typical loop. So we say for epoch in range num epochs, and so this will loop over the epochs, and now we loop over all the batches. So here we say for I, and then again we unpack this. So we say images and labels, and then we iterate over, enumerate over our train loader. So the enumerate function will give us the actual index and then the data, and the data here is the tuple of the images and the labels. And now we have to reshape our images first, because if we have a look at the shape, then we see that this is 100 by 1 by 28 by 28, as I showed you in the beginning. And now we set our input size is 784. So our images tensor needs the size 100 by and 784 as second dimension. So the number of batches first. So let's reshape our tensor first. So we can do this by saying images equals images.reshape, and here we put in -1 as the first dimension. So then tensor can find out this automatically for us. And here as second dimension, we want to have 28 by 28. And then we also call to device. So we will push this to the GPU if it is available. And we also have to push the labels to the device. So labels equals labels to device. And now let's do the forward pass. So first we do the forward pass and afterwards the backward pass. So the forward pass, we simply say outputs equals model, and this will get the images. And then we calculate the loss by saying loss equals, and then here we call our criterion, and this will get the predicted outputs and the actual labels. So this is the forward pass, and then in the backward pass, the first thing we want to do is call optimizer.zeroGrad to empty the values in the gradient attribute. And then we can do the next step by saying loss.backward. So this will do the back propagation, and now we can call optimizer.step. So this will do an update step and update the parameters for us. And now let's also print the loss. So let's say if I plus 1 modulo 100 equals 0. So every 100th step we want to print some information. So let's print the current epoch. So by saying this is epoch plus 1, and then we want to print all the epochs, so number of epochs. Then let's also print the current step by saying step, and this is I plus 1. And then the total number of steps by saying n total steps. And we also want to print the loss by saying loss equals loss.item. And let's also say we only want to print 4 decimal values. So yeah, now we are done with the training. So this is the whole training loop. And now let's do the testing and the evaluation. And for this, we don't want to compute the gradients for all the steps we do. So we want to wrap this in a with torch.noGrad statement. And then first we say the number of correct predictions equals 0 and the number of samples equals 0 in the beginning. And then we loop over all the batches in the test samples. So we say for images and labels in, and here we can simply say in test loader. And then again we have to reshape this, so like we did here. So images and labels, we want to reshape this and put it and push it to the device. And then let's calculate the predictions by saying outputs equals model. So this is our trained model now, and this will get the test images here. And then let's get the actual predictions by saying underscore and then predictions equals torch.max of the outputs and along the dimension, along the number 1. So the torch.max function will return the value and the index. So we are interested in the actual index. So this is the class label. So that's why we don't need the first actual value. So these are our predictions. And now let's say the number of samples plus equals, and here we say labels dot shape 0. So this will give us the number of samples in the current batch, so should be 100. And then we say the number of correct, so the correct predictions equals, and here we can say predictions equals equals the actual labels, and then dot sum, and then dot item. So for each correct prediction, we will add +1. And then, of course, we have to say plus equals the number of correct values. And then when we are done with the loop, we calculate the total accuracy by saying acc equals 100 times the number of correct predictions divided by the number of samples. So this is the accuracy in %. And now let's print this. So print, and we want to print accuracy equals, and here we simply say acc, and then we are done. So now let's save this and clear this, and let's run this and hope that everything is working. So now our training starts, and we should see that the loss should be increased with every step. Sometimes it will also increase again, but finally it should get lower and lower. And now we should be done, and testing is very fast. So now we see that the accuracy is 94.9, so it worked. Our first feed forward model is done, and yeah, I hope you understood everything and you enjoyed this. If you like it, please subscribe to the channel, and see you next time. Bye.